Section 4.1, to graph sine and cosine functions. The next couple of slides have definitions that I'll read through and place on our group resources. First, we have a periodic function, which is a function of f such that f of x equals f of x plus np, and here for every real number x in the domain of f, every integer n, and some positive real number p. The smallest possible value of p is the period of the function. Well, what does that mean? That means the graphs in this section are periodic, which means the shape repeats themselves exactly after a certain amount of time. And anything that has a regular cycle, like tides, temperatures, rotation of the Earth, can be modeled using a sine or cosine curve. The right side of the screen gives us a unit circle, which we should be familiar with. It has a radian measure of angle or a degree measure of an angle and the associated terminating point on the unit circle itself that represents the sine of a radian measure, which would be the y value, or the cosine of a radian measure, which would be the x value. On the left side, we have an example of the sine curve. The sine curve is generated from the unit circle. It has some constraints. Down here it says the graph is continuous over its entire domain. Therefore, it is continuous over all of the radian measures through one rotation and multiple rotations, be it on the right side of the y-axis, which would be a positive rotation, or the left side, which would be a negative rotation. Its x-intercepts are in the form of n pi, where n is an integer. Its period is 2 pi. Therefore, you can see if it starts at 0, it then will go over one revolution through the unit circle, which would give us the 2 pi. And in that span, it repeats itself on the next section. It would just start repeating itself over and over after that whole period is done. The graph is symmetric with respect to the origin, so the function is an odd function for all x in the domain. This graph is a sine wave or sinusoidal. Let's take a little closer look at the sine function graph. Recall from previous sections that we know the sine of theta is equal to y. So if I start my graph at sine of 0 radians, the y value associated with the sine of 0 radians is equal to 0. Now I just want to go to my quadrant angles because they're the easiest ones to graph. Remember, our quadrant angles are 0 radians, pi over 2 radians or 90 degrees, pi radians or 180 degrees, 3 pi over 2 radians, which is 270 degrees, or 2 pi radians, which is 360 degrees. And recall, we're starting at 0 and going through one revolution of our unit circle. So the sine of 90 degrees or pi over 2 is going to equal 1. The sine of 180 degrees or pi is going to equal 0. The sine of 3 pi over 2 or 270 degrees is going to equal a negative 1. And the sine of 2 pi or one complete revolution is going to equal 0. We can associate that with the unit circle by just taking a look at the diagram. The sine of 0 radians has a y value of 0. The sine of 90 degrees or pi over 2 has a y value of 1. The sine of 180 degrees or pi has a y value of 0. And the sine of 270 degrees and 3 pi over 2 has a y value of a negative 1. And one complete revolution takes us back to 360 degrees, or the sine of 2 pi gives us a y value of 0. That is exactly the graph that we have with our sine function. The sine of 0 is 0. The sine of pi over 2 is 1. The sine of pi is 0. The sine of 3 pi over 2 is a negative 1. And then the sine of 2 pi takes us back to 0 again. And then it would just repeat itself as we continue around the circle in multiple revolutions. What we have looked is at a static diagram of the sine function. Let's look at one and see how it actually is generated. Here I have the sine function already designated for this diagram. Notice the unit circle is going to start at 0 radians, therefore sine of 0 radians equals a y value that's associated with that, and that's also 0. But if I actually take this and you can watch both the unit circle and the generation of the sine function, and drag this to the right, you can see as my point on the terminal side of my unit circle increases to the sine of pi over 2, or 90 degrees, it takes us to the highest point in that graph, which is 1. Sine of pi over 90, the sine of pi over 2 is 1. Then we continue through quadrant 2. Sine is still positive because in quadrant 2 the y value is positive until we get to the sine of pi, or 180 degrees, and the value associated with that is going to give me a y value of 0. Now in quadrant 3, the sine function is going to turn negative because the y values are negative, and when I get to the sine of 3 pi over 2, or 270 degrees, it's the lowest value it can be, which is a negative 1. Then we'll continue into quadrant 4. My y value is going to be negative again until we continue up to the full revolution of sine of 2 pi, or 360 degrees, and that gives us one complete rotation of the circle, and therefore now that is a period because it will start repeating itself as I continue through. This next slide represents the graph of the cosine function. Recall that our radian measure with cosine is going to be the values that associate with our x values. Therefore, when I start out on this graph, I'm going to have the cosine of 0 radians. The cosine of 0 radians is going to give us a value of 1. As we continue through, this is just going to generate our quadrant angle measures, and they're going to graph similarly. If I take my sine function, which is at the bottom of the page, and shift that up to the cosine function, we can see that they are images or mirror images of themselves, but the cosine function is translated or moved to the right by 90 degrees, or pi over 2 radians. In this diagram, I have selected cosine, and I'm going to do the same thing as I have done in the past with the sine function and show you how this is generated. Notice at sine of 0, I am at 1. And as I continue through the first quadrant, x is positive, and we finally get to pi over 2, or cosine of pi over 2. I'm going to get a value of 0 for my x. Through quadrant 2, my x values become negative, and when I get to the cosine of pi, or 180 degrees, I'm going to be the negative 1, the lowest value in my function. And I continue to quadrant 3, I'm still negative until I get to 270 degrees. Cosine of 3 pi over 2 is going to give me 0, and then I continue back into quadrant 4, which makes my x value positive, and I will get to 1 revolution, which will be the cosine of 360, or 2 pi, and I'm back to the highest part of my revolution, which is, or function value, which is 1. At that point, you can see I will start repeating my function. Therefore, again, that period is 2 pi. If we take a look at these functions side by side, we might be able to come up with some generalizations to help us graph these. For example, if we take a look at both the sine and cosine graphs, we can see that the y values don't get higher than 1 or lower than a negative 1 on both. And we also can see that on both graphs, for example, on the sine, I start at 0 for the beginning of the period, and I end at 0 at the beginning of the period. In between, I'll have 0, positive 1, negative 1, 0. So I start a period and end the period with the same value. The same thing with the cosine function, that I have a y value of a positive 1, then to a negative 1, and then to a positive 1. I start the function with a value of 1, going to 0, negative 1, 0, and 1, and I end the function with 1. So the periods, or the functions, must start with the same value and also end with the same value, and then they repeat themselves based on their periods. So it seems like we have two things we have to deal with. One is the period of the function, and 2 is how high the function can go or how low the function can go. Those two concepts can help us graph the sine function and the cosine function. For how high and how low the function can go is called the amplitude. The amplitude of a periodic function is half the difference between the max and minimum values. On our last functions, we have the highest value is 1, the lowest value is a -1. That means the total distance between them is 2. Therefore, half of that would be 1, which would say that's how high it can go and that's how low it can go. The graph of y equals a sine x or y equals a cosine x, with a not equal to 0, will have the same shape as the graph of y equals sine x or y equals cosine x, respectively. Let's see how to determine the amplitude of these functions. The a in the expression y equals a sine x represents the amplitude of the graph. So the constant that is out in front of my function is going to tell me how high that function can actually go. It is the indication of how much energy the wave contains. Amplitude is always a positive quantity. We could write this using absolute value. So for me given a function of y equals a sine x, the amplitude is equal to the constant, the absolute value of the constant in front of that function. Therefore, that tells me how high it would go, and that tells me how low it can go. The next slide will show us how to determine the period of a function. Recall that a period of a function is the point at which the graph will start repeating itself. So to determine the period, it says that for b, where b is greater than 0, the graph of y equals sine bx will resemble that of y equals sine x. Notice the only difference between these two functions is the constant b rather than here a constant of 1. Therefore, b will determine the period. So the procedure to do this is to take 2 pi divided by b to determine the period of the sine function. The graph of y equals cosine bx will resemble that of y equals cosine x. Again, the only determining difference here is that I have a constant of 1 for cosine x, and I have a constant of bx. Therefore, b could be any variable between 1 and any number. So again, the period to be determined for cosine is going to be 2 pi divided by b. If I take a look at this next slide, I just want to see the comparison between certain types of functions. So here I have 3 functions. I have p of x, which is sine x. Again, I have a constant in front of 1, therefore its amplitude is 1. I have a constant of 1 inside, which gives me 2 pi divided by b, or 2 pi divided by 1, which is 2 pi. Q of x, my amplitude is 5. But my period is the same since the number inside my function is 1. And r of x equals 10 sine of x. My amplitude is 10, and my period is the same because the constant, again, is similar to the previous functions. So here, the height of my function above and below the axis will be 1. Here it will be 5, and here it will be 10. So if I take a look at these 3 functions, I recall that I start at 0, and as I go through the period, I end with 0. As in all these functions I'm dealing with, what I start with is what I'm going to end with before I start repeating my function, or in other words, the period ends. So if I go here, the 3 functions hit at the quadrant angles, height of 1, 5, and 10. Back to another quadrant angle, they all intersect at 0. To the next quadrant angle, which will be again 1, 5, and 10 until we complete a revolution that completes the period at 2 pi. So the only difference between these functions are the amplitudes, and the periods are the same.